So here we are with a new topic. It's not a new one. It's something linked to what we have discussed in past. And here, what we are supposed to discuss is the interaction, basically the interaction of radiation with atoms, or we can say interaction of fields, magnetic field, electric field, with the atoms. So that's the point, and in this video we will be discussing Zeeman effect, and this Zeeman effect is, to be precise, how these atoms behave, or how does these atoms interact with magnetic field, the magnetic field that's provided outside these atoms, and And to start with, if we have an external magnetic field, B, as we know, it's a vector quantity, and uh, and if we have a magnetic dipole, and if we have something like dipole, magnetic dipole, and this magnetic dipole has an amount of potential energy uh, that depends upon both the magnitude of what's called as dipole moment, and symbolized as mu, uh, and its magnetic field. So so if we have, say, some uniform magnetic field like this, and we have a dipole, and that dipole, say it makes an angle equal to theta. Let us assume this is the direction of magnetic field, and and the torque in this case is simply mu b sine theta. And all we know, this torque is uh, it's 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 the product of dipole moment, magnetic field, and theta is basically the angle. Theta is angle between magnetic moment and magnetic field. Now, this we can see from here that this torque is maximum when this dipole is perpendicular. If I take a projection like this, when this dipole is perpendicular to the field, this torque is maximum. This torque is maximum when this dipole is perpendicular to magnetic field, and it is zero for being this dipole either along the direction of magnetic field, or opposite to the direction of magnetic field. And if we have to calculate the potential energy, uh, then we must first establish a reference configuration in which um is zero. So taking as equal to zero, which is the potential energy, and by definition taking this equal to zero, since only changes in the potential energy are ever experimentally observed, and the choice of a reference configuration is always arbitrary, and choosing to be equal to zero. Now it is convenient to set this potential energy equal to zero. Now, when theta is, if theta is 90 degree, uh, that is this mu, the magnetic moment that we have, it is perpendicular. It's perpendicular to the magnetic field, and the potential energy at any other orientation of mu uh, is basically equal to the external work that must be done to rotate this dipole from 90 degree to the angle theta. So there has to have an angle which I may call as theta 1, and that must be equal to pi by 2. So the potential energy that we have here, we can write down that potential energy as the we can write down that potential energy as the integral of this torque over the angle d theta, and starting from 90 degree to theta. So on integrating this, when we'll integrate this, what we are going to get is we will have mu and b will be out, and we will have sine theta. What's that? Integration of sine theta. That will be integral of sine theta d theta from pi by 2 to some theta. So this will come up as minus mu b cos theta. So here this mu points in the same direction as that of magnetic field. And then what will be in that case? In that case, we will have this potential energy will be minus mu b. That should be the case, and this is what executes the fact that the magnetic field tends to align itself with an external magnetic field, and the magnetic moment of the orbital electron that we have. So we have an orbital electron, taking into account, say hydrogen atom. The magnetic moment of the orbital electron in hydrogen atom certainly depends on its angular momentum. And hence both the magnitude of the angular momentum and its orientation with respect to the field, they determine the extent of the magnetic contribution to the total energy of the atom. Now, when this electron that's revolving, when it is in some magnetic field, it will have magnetic moment associated with it, and that magnetic moment, if I assume that is mu, that will be the product of current and the area of that loop. And if I proceed from here for this magnetic moment, which is basically the product of current and the area of the loop under consideration, what should I say is that this magnetic moment, I would again write this mu is current into area. Now, what would I like to do is that if I have to define current, I can define current as this electron makes the number of revolutions per second in a circle of radius r. We have a circle and it has a radius equal to r, and this electron is orbiting, and this current that we have, this current can be written as minus E and nu refers to the frequency with which this electron is orbiting, and this negative sign is a consequence of charge of the electron. So to say what will be magnetic moment, if I use for I minus E nu, and for current I have pi r square, because I'm assuming a circle of radius r. So this is my magnetic moment. Now, if I have to define some linear speed, if I define the speed as nu of the electrons is 2 pi nu r. Okay, so defining the linear speed nu of the electron is 2 pi nu r, then its angular momentum will be L is mvr. And for v, I have, this is not nu, this is v, and for v what we have is m times 2 pi 2 pi uh, 2 pi nu r square. That should be the case. 2 pi nu r square. So if I compare the formulas for magnetic moment that I have here and angular momentum what will I have? So for angular, what will I have? I will have for angular momentum, I have L is equal to mvr, and for magnetic moment, I have uh, uh, for angular momentum, I have 2 pi m nu r square is my magnetic moment. Yeah. No, this is not magnetic moment. This is angular momentum. Sorry, this is wrong. So this is angular momentum, and magnetic moment is here. And if I take the magnitude of magnetic moment, no, let me take the magnetic moment mu, that is minus e nu pi r square, and say this is equation A and this is equation B, and let's correlate the two equations and obtain the relation between magnetic moment and angular momentum. So doing so, what we will have is we can write down L by mu is m times 2 pi nu r square by E nu pi r square minus. Okay, we will have some cancellations here. This nu and nu, r square and r square will go, and this pi and pi will go. So if I take mu on the one side, I will have minus E by 2m times L. So this is the relation between the magnetic moment of electron revolving around and and its angular momentum. So what is this mu now representative of magnetic moment of this electron? So to speak, what we have is we started from a looping electron, and we defined mu as current into area, and and after these calculations that we have come up, we have obtained the magnetic moment for this electron in terms of angular momentum. That's E by 2m times L. That's the case, and we can think of the directions of magnetic field. We can think of the field directions here, and because of the looping of this electron in the circular orbit. So we have so what we have now is the equation for magnetic moment of electron. Now this quantity that we have, this minus E by 2m, this minus E by 2m, which only involves what it involves is the charge of electron and mass of the electron, and this ratio that we have here, this is called as gyromagnetic ratio. Gyromagnetic ratio. All right, and the negative sign is if we have to go with negative sign here, what it means is that this dipole moment that we have, it is in opposite direction to the angular momentum, because we have mu is minus E by 2m times L. They are the vectors. We know them by definition, and 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 this expression for the magnetic moment of an orbital electron, we have achieved this result through the classical means, through the classical calculations. Now, if we now if we inculcate the quantum mechanics and quantum mechanics, the quantum mechanics gives the same results that we have obtained through classical means here. And the magnetic potential energy of an atom in a magnetic field here is um is E by 2m times LB cos theta. And we can see here that this potential energy, it depends on both angular momentum, magnetic field, and it depends on theta. Okay, so there's an addition of magnetic field and cos theta. So now proceeding on with more insight into the problem. If we go with the basic relation for cos theta, from the diagram that we started with, we had a dipole and we had the magnetic field, and from that diagram, uh, we can we can have this cos theta as ml by under root of L times L plus 1. All right, and where this under root term is basically the angular momentum. This is L is under root of L times L plus 1. And to find this L, we have H cross, we have missed it, okay? So this L is under root of L into L plus 1 times H cross. Now, what we would like to do is, in order to obtain the magnetic energy that an atom of magnetic quantum number having equal to ml, when we apply the magnetic field, we put this cos theta that we have, we put the above expression that we have here, we put it into the original equation. We put it into the equation here. So using for cos theta, the thing that we have here, and what we are going to get is we're going to get the magnetic energy. So proceeding from here, what we get is we get um is ml times E H cross by 2m times B. And this EH cross by 2m, this is called Bohr magneton. This is called Bohr magneton. And the value of this Bohr magneton is mu B. It is EH cross by 2m, and its value is it is 9.274 times 10 to the power of minus 24 joule per Tesla. Okay, so in a magnetic field, what we have, when we have something, an atom in a magnetic field, the energy of the particular atomic state depends on the value of ml. And if it depends on the value of ml, that means it depends on the value of n, the principal quantum number. A state of total quantum number that we have, n, it breaks up into several substates. And when the atom is in magnetic field, and their energies are slightly more or slightly less than the energy of the state in absence of the field, what happens is this leads to what's called as splitting. This leads to the splitting of individual spectral lines. All right, uh, and you have splitting of spectral lines into some separate lines, and when atoms radiate in magnetic field, and at the same time, the spacing of these lines that we have for one, where we have many lines, the spacing of the lines depends on the magnitude of magnetic field that's applied. And this splitting of spectral lines by virtue of magnetic field is generally called as Zeeman effect. And this splitting comes in action because of this ML. If there is absence of ML, what we have in classical equation, then you cannot expect the splitting of these spectral lines. But this ML can have it can have a range of values that's how this ML contributes to the splitting of these spectral lines when an external magnetic field is applied. And this Zeeman effect was a complete experimental confirmation of space quantization. Space quantization. Now, because as I told you that things are happening because of this ML that's being introduced in the equation. Now because this ML can have how many values it can have? It can have 2L plus 1 values. All I can say, it can have plus L via 0 to minus L of values. And and in this state of the given orbital quantum number, L is split into 2L plus 1 states, and that differ in energy. There is difference of energy in that splitting. There is a difference of that energy. What's that? That is mu B and B. This much of difference of energy when the atoms are in magnetic field. However, because changes in ML are restricted, so you cannot have all possible values for ML. The changes for ML are restricted. What they are 0 or plus minus 1. These are the allowed values for these magnetic quantum numbers. Therefore, the spectral lines form a transition between the two states of different L to be split into only 3 components. We have 3 components that we can see, and splitting into the 3 components is called as normal Zeeman effect. And this normal Zeeman effect consists of splitting of spectral lines of frequency. If we have the original frequency, say nu naught, this nu naught splits into the 3 components: nu 1 and 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 nu 2 and nu 3. And nu 1 is nu naught minus mu b by h, and nu 2 is the original frequency nu naught, and nu 3 is nu naught plus mu b by h. Now this is simply nu naught minus e by 4 pi m b, and this is nu naught plus e by 4 pi m b. So this will be the splitting in the normal Zeeman effect that will be observable. Now, if I have to tabulate this thing, this normal Zeeman effect, I would like to what I have, if I choose a line for for L equal to 2. And this line will split, okay, into many lines as I'm trying to to illustrate here. and 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 it will go like this. So for this I will have ml equal to 2, then here I will have 1, then I will have 0, then I'll have -1, and then I'll have -2, and I will have another state that is L equal to 1, and this will be H nu naught when you're not applying any magnetic field, no B. And when you're applying the magnetic field, what's happening is you have the splitting as for L is equal to 2 state, and for L is equal to 1. It will go like this. Trying my level best, it will go like this. And what I'll have here is ml equals 1. This is ml equals 0. This will give me ml equal to -1. And we can see that we will have the transitions that we can talk about, say a transition like this, and a transition like this, and a transition like this. And this can be a one set of example for a transition. This transition will this set of transition will lead to H nu naught minus E H cross B by 2m. And here for this set of situation, we will have delta ml changing by +1, and the same state can be developed for delta ml equal to 0, and we can develop another line with delta ml equal to -1. So to say, what we will have from this splitting is that in normal Zeeman effect we have a spectral line of frequency nu naught, and it splits into the three components when the radiating atoms are in magnetic field. Okay, and one component is nu naught, and the others are less than and the greater than that of that nu naught that we are talking about. So there are only three components because of the selection rule that I have tried to show here. So what we are getting something like this. We have an original frequency nu naught, and you are not applying any magnetic field, no magnetic field. And when you apply the magnetic field, you have the spectrum. You have the spectrum here. This should be called a spectrum. And you have frequency 1, you have frequency 2, and you have frequency 3. So this one is the original frequency. And then you have nu naught minus EB by 4 pi m. And then you have nu naught plus EB by 4 pi m. So this is how I tried to demonstrate Zeeman effect, and what we had tried to understand here is the interaction of magnetic field with atoms, and what we have found in case of normal Zeeman effect, what happens, the original line splits into the three lines. In one case, the frequency of the line is greater than that of the original one, and in the other case, the frequency is less than that of the original frequency. So with this, I would like to say goodbye and good luck.